All right, Rolle's theorem and mean value theorem. Rolle's theorem is just a special case of mean value theorem. But we'll start with Rolle's theorem. So let f be continuous on the closed interval a comma b and differentiable on the open interval a comma b. If f of a is equal to f of b, so the output of a is equal to the output of b, then there's at least one number c in a comma b such that f prime of c, so the derivative at c, is equal to 0. All right, here's what that looks like. A comma b. So f of a is equal to f of b. So they are at the same output. So there is some place, if this function is continuous on that interval, a to b, then the function is differentiable. So there is some place C where the slope, the IROC, is equal to 0. So f prime of C is equal to 0. Okay. What happens is that it's basically the slope of these 2 points. So the average rate of change between A and B is 0. So there's some place on the graph between those two values where the slope is also going to be 0. All right, let's try. Show that Rolle's theorem applies to f of x on the interval 1, 2. Find the value of c guaranteed by Rolle's theorem. So the first thing is we have to prove that we can use Rolle's theorem. And one of the conditions is that we have to have an equal value at a of b or f of b and f of a. So I'm going to go ahead and do that. I'm going to check. Is f of a equal to f of b? So f of a is f of 1. And I'm going to calculate it. So 1 squared minus 3 times 1 plus 2 is 0. And f of 2, the other endpoint, is 2 squared minus 3 times 2 plus 2. And that also equals 0. So I can see that f of a is equal to f of 1 is equal to f of 2. So f of a is equal to f of b. All right, that's the first thing we have to check. The second condition is that f has to be continuous and differentiable on the interval. So I have to actually write it on my paper. I know that a parabola is continuous, and it doesn't have any vertical tangent lines or sharp turns. So it's going to be differentiable and continuous on all x values, but specifically on the interval, the closed interval 1, 2. So because of these three things, 1, 2, 3, I'd say therefore Rolle's theorem applies. Like, I can use this thing. So what I need to do next is, so that's all the checking stuff to make sure I can use Rolle's theorem. Then I find the derivative, 2x minus 3. And I know that at some point on that derivative, there's going to be a value c where the derivative is equal to 0. So I say 0. So it guarantees that there's going to be a derivative that's equal to 0. All right, so I get x is equal to 3 over 2, which in Rolle's theorem is my value of c. So I get f prime of 3 halves is equal to 0. That's my c, and that's my 0. And that's it. That's the value c that's guaranteed. All right, so Rolle's theorem is a special case, so when the derivative is equal to 0, of this other theorem, mean value theorem. It says if the f is continuous on the closed interval a comma b and differentiable on the open interval a comma b, sounds familiar, then there exists a number c, so a value c, between a and b such that f prime of c is equal to f of b minus f of a over b minus a. This is a fancy way to say that the instantaneous rate of change at c is equal to the average rate of change of the endpoints. So there's, okay, so the IROC is equal to the AROC. That's mean value theorem. Here's a picture for you. So we have a closed interval between A and B, okay, A and B. And if I take the average rate of change between A of B, if the function is continuous and differentiable, so it doesn't have any sharp turns or undefined points, undefined points, then we have somewhere along this curve, the tangent line slope is going to equal the secant line slope, okay? So another way to say this is that the tangent line slope, there's somewhere where the tangent slope will equal the secant slope. All right, let's do some examples. All right, so suppose we know that f of x is continuous and differentiable on 6, 15. Okay, so look, we already have our conditions here. We also know that f of 6 is equal to negative 2, and f prime of x is less than or equal to 10 for the interval. What is the largest possible value of f of 15? So I'm going to be like, I have my instantaneous rate of change, and I just have a value. So I'm going to be like, I can use the theorem, the mean value theorem. So the average rate of change has to equal, where does that equal the instantaneous rate of change? So my interval is, this is my A and my B, 6 and 15. So for average rate of change, that would be f of 15 minus f of 6 over 15 minus 6. And I want that to be less than or equal to my instantaneous rate of change, which is 10. Okay. Now we just simplify. So I get f of 15 minus 2, which is 2, over 9 is less than or equal to 10. Okay, lastly, we're going to do some solving. So f of 15 is equal to, multiply by 9 and subtract 2, so 90 minus 2. So f of 15, oops, not an equals, less than or equal to, has to be less than or equal to 88. So what is the largest possible value for f of 15? It would be 88, okay, 88. All right. Determine all the numbers C which satisfy the conclusion for the mean value theorem for f on the interval -1, 2. Okay, so we have to start with our conditions. So, oh, you can't see that. We have to start with our conditions. Is this function f differentiable and continuous on the interval? It's a cube function, so yes, there's no sharp turns, there's no undefined points. Okay, so f is differentiable and continuous on the interval. So mean value theorem applies, which means that AROC at some point will equal to IROC. This is not official. I just remember that in my head. All right, so I am going to figure out what f of 1, f of -1, and f of 2 are really quick since I need those to find the slope. So I get -2 and 14. And now I'm going to set up my mean value theorem. I know f of 2 minus f of negative 1 over 2 minus negative 1 is equal to the instantaneous rate of change, which is going to be f prime of c. So the instantaneous rate of change at some x value. Now we have to figure out what the average rate of change is. So I'm going to do 14 minus 2. Nope, I said that wrong. This one is a positive 2. So it's 14 minus 2 over 3 is equal to f prime of c. So I get 12 over 3 is 4 is the average rate of change. Okay, remember this is my average rate of change. And I need to figure out when does the instantaneous rate of change at x equals c, like what x value are we talking about? When is the instantaneous rate of change equal to the average rate of change? So the last part would be to set my f prime of x equal to 4. So at what x value? So I need to take a derivative. F prime of x is equal to 3x squared plus 4x minus 1. So I get 3x squared plus 4x minus 1 is equal to 4 quadratic. So we're going to solve 4x minus 5 is equal to 0. I used polysmelt on my calculator to solve. You could use quadratic formula. Seems like it would take a long time, but polysmelt. Okay, so I get x is about equal to 0.786 and x is about equal to negative 2.120. And then the negative value is not in the interval. So I know that at x is about equal to 0.786, the average rate of change is equal to the instantaneous rate of change. Okay. All right, the last one. Ben rides a unicycle back and forth in along a straight east-west track. That's skill. The twice differentiable function b models Ben's position on the track. The table below gives values for b of t and Ben's velocity. For 40 is less than t, or less than or equal to t, which is less than or equal to 60, must there be a time when Ben's velocity is 2 meters per second? So must there be? This is like, can we guarantee that there is a velocity of 2? So b of t is the position function, v of t is the velocity function. So we are really straight going to use mean value theorem here. Okay. It also says the reason why we know we can use mean value theorem is that it says that the function is twice differentiable. So because the function is differentiable, it is also continuous. So I have the mean value theorem, which I can use, is a rock is equal to I rock. So I want for the interval 40 to 60, I want to find the average rate of change. So I'm going to do the position, b of 60, minus his other position, b of 40, all over the total time, so, or the difference in time, 60 minus 40, right? And that is going to equal b prime, which is also v of t. So at what time? Next up is to substitute. So b of 60 is 49. B of 40 is 9 over 20 is equal to v of some value at some time. Okay. So 40, looks like 40 over 20 is 2 v of t. So look, since we can use the mean value theorem, we know that we can guarantee that Ben's velocity is 2 meters per second at some time between 40 and 60. We just haven't solved for it yet. But we're saying, look, the average rate of change was 2 meters per. I did a really bad job on the units last time, so I'm going to try really hard. Is meters per second. So there is some instantaneous rate of change on the curve that is also 2 meters per second. So we're going to write because b of t is differentiable and continuous on the interval, the mean value theorem guarantees. So all these theorems are about guarantees. A time in the interval that the velocity of t is equal to 2 meters per second. All right, so we just checked off our guarantee. All right, that's the mean value theorem. I'll see you guys later.